Hello everyone, welcome back on the course of Hyatt Surveying, and we are in module 6 photogrammetry. We have already completed 5 lectures in this module. In the last lecture, we have discussed about space resection, space intersection. The combination of two is called areal triangulation. Further, we talked about bundle adjustment and self-calibrating bundle adjustment. Apart from this, we also learned what is absolute orientation and what is relative orientation. We have learned computational photogrammetry, how computer works for you if you are using photogrammetry for stereo images. Now, let us assume that we have done computational work completely and we have created 3D coordinates. That means, we have done some measurement on our stereo pairs, that is x1, y1 and x2, y2, two image coordinates, or maybe more image coordinates if there are more number of stereo images for one point. And then using all those points, we find out what is the 3D coordinates of the terrain point, space intersection process. So, let us start with 3D points that we have calculated as a part of space intersection process. And today we are going to discuss about the photogrammetric products. There are two products, digital elevation model and ortho map, ortho image or ortho photo. So, let us start. There are 4 books. This book is available in India. In the last lecture, we talked about control point, terrain point, and so there was a terminology for a ground point XP, YP and ZP. Now, let us say there is a terrain given like this. There are points like this which are uniformly distributed, and for this terrain, you want to create 3D coordinates for some points. So, let us say that you have collected these points with very high accuracy using DGPS or maybe map. There are 100 points you have collected in the field and you know the accuracy of those points. Out of those 100 points, divide these points into 2 slots equally, and remember these 50 points are also uniformly distributed on the terrain. That means, let us say I am collecting these points which are uniformly distributed. So, you can now see that remaining points which are plus marked without triangle, they are also uniformly distributed over the terrain. This is batch A and this is batch B. So, I used batch A 50 points for space resection. Remember, these 50 points are more than our minimum number of points which are required for the space resection. The number of points are more than the minimum one, I will go for the least squared solution and I will find out exterior orientation parameters, and if I am using a self calibrating bundle adjustment, then I will determine IO parameters also. Not only that, using error propagation, I will find out what is the sigma EO and sigma IO. So, that is the confidence or variance covariance matrix of EO and IO parameters. Here you can understand that these sigma values are going to give quality of the parameters. In general, these points are called control points or ground control points or GCPs. These ground control points are used for the calculation of parameters EO and IO parameters, or developing a mathematical model for image and object relationship. Now, these points are generally indicated by triangle or there is a dot inside triangle. Both conventions are there, they are GCPs. Where this term control points is used, photogrammetry is being used by mechanical engineers, medical science people. They do not collect the point on the surface of terrain, rather they collect the point on the surface of a body or surface of a machine. So, that is why they use the term control point. However, in photogrammetry for terrain mapping, we always use the term ground control point. What about batch B? There are remaining 50 points. I will now do the space intersection for those 50 points. I already know the XYZ from the DGPS survey or the map. Also, I am determining this, let us say x hat, y hat and z hat for I points. Now, I can find out the accuracy on these points because I have the XYZ from the field and I am calculating x hat, y hat and z hat using space intersection. In the space intersection, I have used these EO and IO parameters. So now calculate the 3D error and accuracy xi minus xi hat square plus yi minus yi hat square plus zi minus zi hat square, and under root is there. Then summation sign, if we are doing for 50 points, so divide by 50, this is RMSE error. Similarly, I can also find out RMSE for xy, like xi minus xi hat square plus yi minus yi hat divided by 50, and RMSE z, zi minus, here it is summation, right, zi minus zi hat square summation over 50 points and divide by 50. And now that is the quality of work here, or the quality of prediction. And these 50 points which are used for the space intersection, I call them checkpoints because I have used them for the accuracy analysis or the accuracy evaluation. Remember, 50 is not a limit. Sometimes you need 500 points also. So don't stick to the point 50 here. So these points are called checkpoints and they are indicated by square like this. So once I evaluate the accuracy over those 50 points, I know what is the accuracy of prediction. I will get some RMSE z here, that is vertical accuracy of the prediction, or I also know what is planimetric accuracy. Now, if I use n number of other points which are not these 100 points, where I am taking image coordinates and then using photogrammetric concept, I am predicting their coordinates x, y and z. Based on this performance of the checkpoints, I can now confidently say that each of these n number of points are calculated with sigma xy accuracy, sigma z accuracy. Now, such a point like these points, I call them tie point and they are indicated by circle or maybe circle with a dot. So, there are third type of points called tie points in photogrammetry. So, now we have three type of points: ground control points which are used for the space resection. Now, we have checkpoints where we evaluate the accuracy of space intersection, and then we have tie points where we generate the 3D coordinates. And finally, let us say we have n number of tie points. It could be 1000, it could be 500, it could be whatever as per the resolution or as per your demand. And they are coming from some accuracy called sigma z and sigma xy, where sigma xy is RMSE xy and sigma z is RMSE z evaluated over the checkpoints. So, this concept should be very, very clear to you. So, let us see, we have generated the 3D coordinates of tie points. However, at each and every point of the image, I have not calculated the tie points or the 3D coordinates of tie points. So, using those points for which I have calculated 3D coordinates, I will do the interpolation, and the interpolation successfully creates this kind of grid. And this grid kind of system where each value on the xy pixel is indicating height, it's called DEM, and that is first product of the photogrammetry. So, let us say we have calculated our 3D coordinates, and after that we have created this kind of grids by interpolation. This pixel is indicating the height of this building. Similarly, this pixel is indicating the height of this building, and all 4 pixels are indicating building. So, digital elevation model, its representation of the earth surface elevation as an array of points. For the purpose of interpolation, these are the points I obtained from the DEM like this. So, this is spacing of the DEM. Yes, this is not a uniform, which is not true. Generally, we have uniform spacing in case of DEM. So, let us assume that these points are generated by DEM at uniform spacing. That means pixel size of the DEM is fixed. Now, you can see here, this is actual terrain which is shown by the red line. The DEM points are these black dots, that this is the pixel of DEM, and here this is the pixel of DEM here. Just assume that they are uniformly distributed. This is the point here and this is the point here. From here to here, this is the real terrain which I am following. However, I have to interpolate it like this. This is interpolated length. I am assuming straight line between the two, not the curved line. but real terrain is the curved. So DEM is according to its resolution and accuracy. It is close to the true representation of the terrain. And that's why we need to have some kind of accuracy measure also for the DEM. What's the Z accuracy, what is planimetric accuracy, and decide the cell size or the resolution of DEM. You should understand these aspects very clearly, because let us say that you have generated some 3D time points using space intersection process, and now you want to generate a DEM as a product to give to your client or to give to your research community or to use it for a research project. Then what should be the cell size or the resolution of DEM? And for that purpose, you should understand accuracy of your 3D coordinates that is given by the space intersection. So once you know that, you can decide what is planimetric cell size and what is vertical resolution or the vertical accuracy of DEM. So let us say these are the grids we have generated, and now if I remove these buildings, this is DEM. So each and every grid is telling some height information as well as XY information where it is situated. So the planimetric location XY and the Z information. And if I use the DGPS, these heights are indicating ellipsoidal height. But if I use the orthometric height in my GCPs, then these heights are indicating the orthometric height of the building. This is the footprint of the building here. Similarly, I have another building here, and this is the footprint. Same way, we have some footprints here, and for this building, we have footprint here. And for this building, where we have 3 towers, we have footprint here. Now, what about this line? Yes, DEM assumes that they are vertically connected, they are linearly connected. Although we know that's building, but however, in case of real terrain, these curves are not very straight, not guaranteed to be straight. Most of the time, they are very, very curvilinear. And so, we should be very, very careful if we do the terrain survey by photogrammetry in the field or in forest or in somewhere natural ground or in the urban area. So according to the situation or according to terrain, we should understand these aspects. This is again the vertical here. We know that for a building, this should be vertical walls. So we should interpolate it like that only. Similarly, I can draw for other buildings. Now, let us look for a real ground, a natural ground, which is curvilinear, which is having some slope, which is having some upslope and so on. So this is the DEM representing the terrain. Here you see 1 pixel is representing the Z value, and this center value is on the map. Here it is representing the XY value. I need not to repeat it again and again. Remember that each and every cell of the DEM is of uniform size. So perhaps it is appearing to you that they are of non-uniform size here. In fact, they are always of uniform size. So be careful on that part. It is just a representation on the screen. We are not efficient to draw all this thing. That's why we are taking help of some kind of curved lines and so on. Now, if you see here that a DEM is collection of Z values at a given XY location. So I can also represent the DEM with the help of some gray image or grayscale image. What's a grayscale image? Let us say you have an image just like any ordinary colored image. Colored image has 3 bands, red, blue and green. Let us say you have only simple 8-bit black and white monitor where you can see the black color as 0 and white color as 255. You have some kind of 8-bit scale where you say that so many variations are possible. It is bit number. I can show colors or any variable by these numbers. The whole range of the elevation I will discretize into these 255 bands from 0 to 255. Each of these 255 bands will represent a certain range of height. I will assign each band one color. So the 0 is black and 255 is white. So according to the shade of the gray will vary height. Higher the height, that means if the elevation is reaching towards the maximum elevation, color will go to the white. So here you can see this is a white color here showing the maximum elevation, and it is black color here showing the minimum elevation. And the minimum elevation for this DEM is 506 meters and highest is 7493 meter. This is a typical DEM of Himalayas. And we have taken this image from United States Geological Survey website to explain what's the concept of DEM. DEM is this kind of representation also. At this point, this is X value here, this is Y value here, and this color value is giving the Z value. Now you can understand that DEM is just a representation of X, Y and Z, a 3D representation, but it does not indicate you any other information. We have created this 3D DEM using photogrammetry, and photogrammetry gives one more information, that is texture. And texture is so important for us because it's our natural tendency to identify the features, objects with the help of texture. Today I am wearing black shirt. This pen is of black color. This screen is appearing white to me. This mobile phone has some white color on the screen. I can capture the photo using this mobile phone and this photo will be colored. So we have different colors and so on. So I can straight away say, in this room there is a clock here, there is some lights here, there is an air condition here, and there is some wooden piece here, and there is one tablet unit here, and there is a table here which is of cream color. So all this color perception we have, and this color perception makes us very intelligent to identify any feature in the field also. I can find out what's a glacier, what's a tree, what's a building, what's the sand, what is a brick, what is the mud, what's the water, what is green or what is blue, what is some kind of muddy or not. All these things are possible with color only. And we should derive the advantage of photogrammetry now. I can wrap up image over the DEM. But before we do that, let us understand DEM with its accuracy limits. First of all, we have the stereoscopic accuracy. Remember, we have stereoscopic concept. This accuracy is divided into two parts: planimetric accuracy, vertical accuracy. So let us talk about planimetric accuracy first. So planimetric accuracy is given by sigma I times MB is called the image scale factor, and it is not the ratio, the size of the pixel on the sensor to the size of the GSD on the ground. Generally, we take an average size of the GSD or average size of a pixel on the ground. Now, the sigma I is image measurement accuracy. What's the image measurement accuracy? When I measure some point on the image, I commit some mistake there in picking up the point. That is called the image measurement accuracy. This could be 1 pixel. If I am doing manual work, this could be as good as 0.1 pixel if I am doing automated type point generation or automated control point generation or automated point selection. There are many other sources of errors that finally give some kind of accuracy. Number of pixels. So I divide px pixel size. So I am expressing my sigma I in terms of pixels. So many pixels, that means 2 pixels, 3 pixels, 0.9 pixel or 0.1 pixel. So I am playing with a factor called k such that I can generate 0.1 pixel, 1 pixel or 2 pixel, whatever I want. K factor is like that. So for 2 pixels, k is equal to 0.5. So 1 upon 0.5 is equal to 2, so 2 times px. I have 2 pixel accuracy. Then I have k factor for 0.1, it will be k equal to 10. Automatically 1 upon 10 become 0.1 and I will have accuracy of 0.1 pixel. I have defined sigma I like that. Now if you see carefully, px is a pixel, 1 pixel into mb, which is scale factor, is equal to the GSD. And as a result, I can specify planimetric accuracy in terms of GSD. So how many GSDs are there? It is 0.1 GSD or 2 GSD, 1 GSD, whatever. It depends on k factor k, and that comes by experience. Now, what is vertical accuracy? Planimetric measurement or the point picking is a major factor that contributes the error. So this is expression for the vertical accuracy, where this sigma px is the error due to the parallax, which I already evaluated here, and this MB is again scale factor. And further, if you see, the vertical accuracy is multiplied with this factor h by b, where we call the b by h base to flying height ratio. More popularly is called base to height ratio. Remember, this is my flying base or air base. It is inverse of the base to height ratio. In general, base to height ratio is recommended to be more than 0.6. So if you put it here, this factor is going to be more than 1, h by b. Now I can replace h by b by f by b, focal length to image base, and then I can still write sigma z is equal to GSD time k factor could be 0.1, could be 2, it is sigma px, parallax error in the horizontal measurement, that is vertical accuracy. So now you can understand what is the accuracy of a DEM. I can also find out the accuracy of space intersection process, which will be little complicated, but these are very simple process to give some estimate of the accuracy of DEM. So far we have determined the accuracy by the estimates or by some kind of mathematical calculation. In reality, we have to find it in the field also, and that is what we call experimental accuracy. In case of experimental accuracy, this is SI, not the sigma I. SI is again some ratio of pixel to the k. I already know this thing, px. I can say SXY is again equal to GSD by k. GSD I can measure in the field as I measure px in the image, or on the ground is GSD. So when I verify or validate accuracies using DGPS on a checkpoints, I can say what's the value of k. So let us say you find out GSD is 10 centimeter and you find out SXY is equal to, let's say, 17 centimeter. Now you can say what is the value of k. K is 10 upon 17. Okay, the moment you put it, you will get accuracies are almost 1 point GSD. I hope you got the idea what's the experimental accuracy. So remember, these accuracies are determined with the help of field surveys, RMSE accuracy, or after determining RMSE accuracy, you are generating a simple rule work. Similarly, you determine not only XY, you determine SZ also in the field as a relationship of, let's say, K2. That means how many pixels are there to indicate what is the ratio of GSD to the K2 and so on. And let us say that in general this idea is there that this factor should be equal to 1, base to height ratio and ratio of planimetric accuracy in field to vertical accuracy in field, not the estimated one. In general, that's the kind of expectation we have from our work. So SZ is a measured vertical accuracy. It is not estimated vertical accuracy. It is measured in field and verified and validated in the field. You have calculated the sigma z, SZ. So what should be the resolution of DEM? That's a surprising question, and most of the people make a mistake here. Let us have the SZ accuracy as RMSE value. So create a DEM of SZ. Now a computer can always do whatever you like, but it's physical interpretation that should give you the real idea. Imagine that you have SZ accuracy and this is the point you are reporting. That means this point can be, let's say, horizontal plane, vertically up by SZ, that is plus, and this could be vertically down, that is minus SZ. Similarly, when I write SXY, it can be on this side or it can be on this side. When I pick a point, I may commit a mistake, maybe positive or negative, and hence you know that we have a limitation here. If I commit a mistake, it will be minimum by 1 pixel. I cannot be within 1 pixel because we count 1, 2, 3, 4 number of pixels. So let's say if I commit by SZ, that means if I am taking a pixel size of XZ or the cell size of SZ, and if I commit a mistake, what will happen? I could be here at this point A, or I could be here at this point B. How can I avoid this thing? Is there any way to avoid? Right, there is a simple way. If I take 3 times SZ cell size or the resolution of DEM, that means instead of 1 pixel here, I take 1.5 pixel here. And let us say the size, big size here, like this. So this 1.5 SZ, again it is 1.5 SZ. I can guarantee you one thing, even if I commit 1 pixel mistake, so either I will be here or either I will be here, but I am always within this cell of resolution of DEM. I hope you got the idea. A simple idea is there. We should always create the cell size or the resolution of the DEM should be minimum 3 times vertical accuracy. If it is 4 times, it's better. In a sense, you are safer side. I hope you are very much sure now. You should always take the 3 times of accuracy in order to deliver a product or in order to claim the accuracy of the product. Because even by mistake, you are here or there, you are within 1 pixel or within 1 cell size or within 1 GSD of that product, maybe DEM or maybe some other product like OrthoMap or whatever. This concept was already explained in the module 4 adjustment computation. So if you have this 3 times this logic, 3 times sigma h less than t, then what will happen? If your client asks 5 centimeter, so you will have a sigma h 5 by 3 centimeter, then even plus sigma h error minus sigma h error, but you are always within this 1.5 sigma h and 1.5 sigma h. And this concept is also applicable to planimetric accuracy. So when you report accuracy from the sigma or from the estimate of the error, always use this 3 times logic. So 3 times of the error should be equal to the accuracy. The next product is OrthoMap. OrthoMap is generated from the DEM, and I already given you one hint couple of minutes before that I want to wrap image onto DEM, because DEM is just the raw value XYZ. It does not give me any other information. It is just a kind of terrain surface representation. But image gives its perfect texture value, and that gives me a real sense of the world. If I wrap the image on the DEM, it is good for visualization, it gives good feel, but at the same time it has some fundamental problem. Image is the perspective projection and the DEM is orthographic projection. So there will be a lot of errors by matching the two. But even if you wrap the image, pixels on the image will not be at correct place. If you have river, it will be on the banks. That means water is appearing on the banks. Maybe building top having some railing, but railing is appearing on the ground. Or the garden on the ground, it is appearing on the building top. So I need to correct image in order to create an orthomap, which is a textured map compared to the topographic map. Topographic map is also a map that gives 3D information or contour information with XY information. But it is a topographic map. It does not give the color information, no texture information. But orthomap that is generated from the photogrammetry, it gives color as well as XY coordinate. Now in case of orthomap, since it is XY coordinate only, so XY coordinate is associated with the some color information. So it's orthomap, it's ortho image, it's orthophoto. When we used to have the photos, we used to have orthophoto. But now we have images, we are using ortho image or ortho map. Basically, it is a planimetric map and it is created from DEM by eliminating sensor tilt and relief effects. In case of stereo pairs, we have relief displacement. If I remove this relief displacement, building top will exactly coincide with the building bottom in the image, and that image will behave like a map. So I can measure distance and areas and determine the locations and features also. That means I can say what is building, what is tree, and where is building, where is tree. There are two types of generation process, forward and backward process. In case of orthophoto generation, input is source image that I acquired during the aerial photography. Then IO and EO parameters of image, they are known. Then we have 3D information about the scene, that is DSM and DTM. DEM is very generic term. Then we have DSM, that is called digital surface model. The digital surface model is representation of the surface, and surface consists of buildings, trees, it could be river, it could be sand, it could be ground, it could be brick and anything. So actual surface of the terrain is represented by DSM. So if I create a product where actual surface is represented, that DEM is called DSM, digital surface model. However, if I remove all the superstructure on the terrain, which means if I remove tree, if I remove building, if I remove any man-made structure, and I am trying to see how the terrain looks like, and that is called the digital terrain model, DTM. For orthophoto generation, I can use DTM or DSM. In case of urban environment, I would prefer to use DSM. But in case of very large scale areas, maybe an upcoming town where buildings are not there, I would like to remove the trees and I would like to use the DTM. For a mega flood modeling, I would like to use DTM and not the DSM, because I would like to know what is the behavior of the terrain with respect to the water flow in flood. Tree may be obstruction there, but tree is not going to decide the flood. But if there is hill, it will decide the flow of the water. So I would like to keep that hill there, but I would like to remove the tree. So I prepare the DTM from DSM by removing all this kind of structure like building, tree and so on. It depends on purpose for which I want to use DTM. So here I can use DTM as well as DSM for the orthophoto generation. We generate DTM or DSM by bilinear interpolation, and for image interpolation we use nearest neighbor, cubic or bilinear interpolation. So what are the error sources? Inaccurate DSM or DTM, occlusion and errors in the orientation parameters. First of all, learn what is forward projection. So let us say there is a point on the DTM or DSM and this is image. And I want to convert this image point into orthophoto map point or orthophoto map pixel. So let us see, this is a DEM, this is a plan grid. On the plan, I am drawing the grid here. It is image where this is point. I calculate for this point what should be the point on the DTM or on the DSM. So I use the collinearity equation where x is image point, r is rotation matrix and lambda is scale factor. And lambda will be deleted if I take the ratio of two equations to third equation. So using that, I will determine x, y and z. Let us say this x, y, z is x hat, y hat and z hat for point P. They are calculated values. I already have this value, so I can find out what is the error here between the two. So that process called forward projection here. Forward projection is little complicated to understand, but we have another process called backward projection, which is quite easy. With the same terminology on capital X and small x, I am going ahead. So this is plan grid and this DEM. This is the point on the surface of DEM, DSM or DTM. Let us say there is an image, and remember we already know EO and IO parameters. So that means I know rotation matrix R or maybe the inverse of R, that is M matrix in the collinearity equation. I project this point from DTM or DSM to the image and I calculate the small x on the image. That means this is input capital X here, this is rotation matrix M, which is a function of EO parameters, and these are IO parameters that I already know. Here it is using EO parameters as known. And S is scale factor. I calculate for this point the pixel coordinate xp hat, yp hat, and we know third dimension is always 0, like this, here 0. So we have determined xp hat, yp hat, and here I have xp and yp. Now I can decide what should be the color at this location, because it is not exactly matching with xp, yp, and that is an error introduced by the numerical process what we are using here. So how to find out the value of pixel or the texture color at this location, which is a calculated location and which is not same as this one. Ideally it should be same if there is 0 error. So we use bilinear interpolation and I will calculate the t value. So this is xp hat and yp hat here minus xi is pixel. So now I am calculating these values like this. And now I am using this, that means if the point is away from the pixel, assign less value to that pixel, or let us take the contribution of all 4 neighbors in some proportion. So these are deciding the proportions, t into 1 minus u, 1 minus t into 1 minus u, and so on. So then I have taken 1, 2, 3 and 4 pixels. So what are the errors that contributed to the orthophoto? So first is the inaccurate DSM or maybe inaccurate DTM. So let us say there is a building on the terrain or on the DSM. However, DSM does not contain, or you have removed it, you have created DTM, and now you are using DTM, you are trying to develop orthophoto. So what will happen? Ideally, this building should be available in ortho image. However, because building is not there, and as a result we will assume that this part of the terrain is flat here. Image has some color. So in the process of orthomap generation, we will assign some color to this whole area. But in fact, the building was this only in the field. I remove the 3D information from DSM. So this is going to incur some error, and that is because of the inaccuracy in the DTM or DSM. And this error is due to occlusion. let us look into the accuracy of the orthophoto. What kind of accuracy should I expect if I using certain DSM or DTM and certain image to prepare ortho image or orthophoto or orthomap? The geometric accuracy of the orthophoto is given by this formula here, that is the total accuracy, and this accuracy is contributed by the mean error resulted by the orientation errors. So, this error is basically resulted by the orientation of the image, because we are bringing image and making it parallel to the DEM. So, basically we are registering image onto the DEM, and that change in the orientation of the image itself creates this error. So, this is a kind of numerical error, and that has to be estimated experimentally or by some numerical process. There is another error that is contributed by the DTM. It is written M ortho DTM, and now two errors are independent to each other. We are making them square, adding them and making the under root, and finally we are estimating the total error here. This is a numerical error, or we need to estimate it by numerical process or maybe by experiments. However, there are some expressions given for the errors caused by the DTM. And here there are two ways to express this error. One is the mean error, or one is the point error. That means I want to find out overall performance and accuracy of orthomap. In that case, what will I do? I will take an overall variation of the terrain or overall error of the DSM or DTM. I will consider that error of DSM or DTM into the overall error of the orthomap. I am just reporting the error of overall product, that is mean error there. However, I can also consider that what is the error from point to point. That means if there is a building, so if I take one corner of the building and try to see what is its position on the orthomap. So, in that case I am trying to estimate the point error for that building corner. Alright. So, let us look into these aspects first. Error in a single point, let us say as I give an example of building corner, it is given by this. Here we can see dz is the height error of the DSM or DTM, and x and y, they are basically the object coordinate, x and y coordinates of corner of a building, and similarly it has z coordinate. So, what is x0, y0 and z0? They are basically the location of the perspective center by the EO parameter x0, y0 and z0, and remaining parameters we are not considering here. So, once we determine the EO parameters, I come to know this. I am observing a point on the ground surface. So, I also know that x, y, z coordinates of that point. So, let us say building corner, and then dz is an error contributed by the DSM or the height error or the elevation error. So, this is the way we estimate the error in the orthophoto, and that is the point error. I can estimate this point error at each and every point by putting this value of x, y and z. So, next is orthophoto error due to the DTM. Now, we are estimating the error or the RMSE point error. That means we can say that each and every point of the orthophoto is having this error, and that is why we are saying that it is a kind of mean error over the whole image. And now imagine that we have a rectangular image which has a side 2A and 2B. Let us say this image of rectangular shape like this. It is 2A and it is 2B. That means B and B here. Similarly, you can divide into two parts, A and A here. With this, I can write this expression, and that is the error in the orthomap contributed by the DTM. So, again I am saying that this is a mean error here of the DTM. It is not a point error. And then if I multiply with this factor, I will have the estimate of a orthomap error. So, now we are having an error in the orthomap, and this estimate is basically applicable to the whole product, which is of this size, 2A by 2A. I hope that you got the idea. What is the H here? It is not a point estimate of the flying height. It is basically average flying height. So, this error basically indicating an average idea or the overall RMSE of the orthomap product. We have to go back after estimating this thing, and we have to estimate the overall error, where we need to put the orientation error also. Okay, as we have said already, that orientation error between the image and DSM has to be estimated by the experiment or numerical way. However, we have done estimate of the error in the orthomap that is contributed purely by DSM or DTM. Then we have given the expression here. One is point estimation and one is the overall estimation or the RMSE for the whole given area. So, that is the idea about the orthomap accuracy, and that is an estimate. Ultimately, we have to go in the field and we have to find out that what is an overall accuracy is there. So, what we will do, we will take some reference data with GPS, and we will take some data from the estimation, and then we'll try to compare them. And that is the way we find out what is the error in locations of different points of features. Now, what is the resolution of orthophoto? The resolution of orthophoto is very simple idea. Errors if given, then create 3 times of error, and that becomes accuracy to be reported. I am giving you one simple example. 20-meter contour interval, many of the researchers commit many mistakes here. From this 20-meter contour interval, they create 2-meter DEM, which is absolutely wrong, not acceptable. You should understand that why this 20-meter decided, because there was some accuracy of this level, 6.5 meter or maybe 6.66 meter, and as a result, if you multiply it by 3, I will get around 19.5 meter, or I can say approximately 20 meter. So that was the reason Survey of India topo sheets have 20-meter contour. Similarly, suppose you find out accuracy of orthophoto, M ortho maybe a point accuracy or point accuracy. You have calculated it and you want to generate, redistribute, or you want to resample your orthophoto, or you want to generate the true orthophoto which is accurate enough, or whatever accuracy is there, it is really giving that accuracy. So what will you do now? Multiply it by 3 and make it equal to resolution, and resample orthophoto, create this resolution. It may not serve purpose in the field, but at least it is very accurate. So whatever purpose you can serve with this kind of orthophoto, this orthophoto is best for that purpose. Let us say 10 centimeter is M ortho. Generate 30 centimeter orthophoto, and with this 30 centimeter orthophoto, whatever you can do it in the field. That means ortho image is of 30 centimeter GSD. You can use this ortho map of 30 centimeter GSD for feature identification on the ground surface. For example, facies of a glacier, or whether banks are vegetated or not. All this kind of stuff you can do, but don't do one mistake. Collecting 5 centimeter information or 5 centimeter GCPs from this ortho map. This is an absolutely wrong idea. So here we stop, we finish, and I can say today that we have learned what is orthomap and DEM or DSM or DTM. With this, now I can confidently say that at least you understand what is the photogrammetry. In the next lecture, we are going to understand some of the photogrammetric procedures that are purely related to digital images and that were not popular because those processors were not invented, and that process is digital image matching. Using digital image matching, we can compare the two images. We can find out the automatic points using digital automated process. I need not to pick the points manually. These are the references we have referred for this lecture, and if someone is more interested, can go to this one. They are good papers, good references for your knowledge also. Thank you.